So this all started with a simple question for us. Now you've heard the announcement from Ken. Inside IBM, we were quite excited by it. But the question to us was, what else could we bring? It's great to come with an announcement, but can we do anything tangible? Could we perhaps simulate a simple power ISA core? Could we synthesize something on an FPGA even? So a couple months ago, we took that idea away and thought about it. Now, firstly, I'd like to point out a bit of background about myself. I'm predominantly a software person. I work with hardware people, but the last line of VHDL I wrote was at college. I wrote a counter. It probably didn't count. I've never had to design any significant hardware. And we only had a couple months to make this happen. Yeah. Would you trust this man to build hardware? I certainly would not. So what we can announce today is something very simple. It's a first step in a journey. We call it microwatt. It's a tiny power core. It's OpenPOWER ISA scalar fixed point subset compliant. It's written in VHDL 2008. It uses an open source toolkit for simulation called GHDL. It uses the Xilinx Vivado toolset for when we want to do FPGA synthesis, and it's not yet available, but it will be shortly available up on GitHub. Very simple by CPU standards. It's single issue, in order. The aim is to be very simple, and we reuse other open hardware components where it makes sense. There was no sense for us to build a UART, for example, so we just pulled it in from the open hardware world. Classic RISC pipeline. We had to stretch it a bit for timing, but I mean, this is textbook what anyone would probably do at college if they'd done hardware, which I hadn't. So we had the makings of a core. What are we going to do next? Well, we've got to run something on it. So why not run MicroPython? Anyone heard of MicroPython before? Yes? No? Good few people. Heard of Python? I hope so. So basically, it's just a very simple embedded interpreter. And the idea here is it's self-contained, it's simple, but it's actually quite useful. And it's used in a lot of places. You'll see it all over the place in the microcontroller and low-end kind of embedded world. So we took MicroPython, and one of the team back home, Michael Newling, ported it to our microwatt core. One of the good things we found was it didn't require any generic changes. Basically, all we had to do was add platform code, which is what you always have to do when you add a new platform to MicroPython, things like the console and stuff like that. And with that, we had basically the makings of a very simple OpenPOWER ISA core. So what we're seeing here is we're just going in to build MicroPython, and it builds and it produces an image. It's basically a RAM image that we can load in. So now we jump into microwatt and we build it. And once we build it, then we basically all we have to do is link in the RAM image that we built from Python and we run it. And basically at that stage, we are interacting with a simulated power core. So this is the compiled VHDL and basically executing instructions as you would on real hardware. It's a little slow, obviously, and hopefully we can add up, and we can. Fantastic. So that was the first step. We've simulated something. What can we do next? Well, next step was enter. I had an FPGA board lying around, and it was a fairly old one. It's a Xilinx Artix FPGA and a little development board from, I think, Digilent. And the question was, can we take that VHDL and can we make it work on top of the FPGA? And turns out we can. So this is just a quick demo of Vivado. We're basically loading up the built VHDL, loading it onto the FPGA, just over the USB. And if we flip across after this point, we get the MicroPython shell. So this is actually running MicroPython now on a FPGA. And the first thing you always want to do is run a hello world. And that runs. Great. We'll also try something a little more stressful than that because that doesn't really prove too much. So we'll just run a quick Fibonacci sequence. So we'll just copy and paste that and then copy it back into the Python interpreter. And it runs. So we've got something now that runs on an FPGA. And so we thought that was pretty cool. That's great. What next? And at that point, well, firstly, I would like to point out, I'm sure you're thinking at the moment, yeah, nice demo, but are there any smoke and mirrors? And I want to tell you today there are absolutely no smoke and mirrors Okay, there are some. So we'll run through that next. There's a few limitations, as with all good demos. We don't have any hardware divide instructions at the moment. We just ran out of time. What we're able to do is basically pull it out of the tool chain temporarily. No reason for that. We can pull in a very simple divider from other open hardware out there. That shouldn't be a problem at all. We're still working on caches and bypassing. As I said, it's very simple, but that should be easy to use. Again, we can pick up some caches from some of the open hardware implementations as well. It's not optimized, it's a proof of concept, but it does work. So at this point, our friends at Xilinx came along and said, can you do anything with one of our great Alveo acceleration cards? So we thought, yeah, we'll give it a go. So they sent it out a couple of weeks ago, and we threw it on, and we managed to make it work. Now, one thing I will point out, if you've used FPGAs before, this is like a chip real estate. Our little core is that little bit of blue. So we thought, we're not even using this FPGA. What can we do next? And so we thought, obviously, how many of our cores can we fit on an FPGA? So at this point, I'll open up for suggestions. How many do you think we managed to fit? 200? 200? I admire your optimism, Hugh. You're wrong. And I've brought koalas, so have a koala. Any other takers?
40.
Who said 40? Wow, you've been prompted. You're correct. Can you catch? In fact, yes, we fit 40 of them on this FPGA. Actually 41, because we had the main CPU. So what are we going to do with this new power that we've found? Well, what are we going to do? Let's think of something interesting. Well, I mean, as I said, these are very simple. They're not coherent. They run just the power ISA fixed point subset. What are we going to run with it? Well, I thought, let's run an accelerator. We'll have 40 accelerators doing something really useful. And I thought, what do I spend most of my time doing every day? And then I thought about it for a while, and I thought, gosh, you know, it seems like each day a new language comes out, and I have to investigate it and look at it. I seem to be writing Hello World applications all the damn time. So I thought, why don't I write a Hello World accelerator? So I've got 40 OpenPOWER cores all running an accelerator. Its job in life is to print Hello World over my Hello World bus. The real reason was I only had a day to come up with this, so I couldn't think of anything better. And so here's a demo. We're basically now using what I think probably about 80+% of the FPGA, so that's pretty good. Sure, we could fit more cores if I had more time. And let's run it. So basically now we're going to we're going to load onto the FPGA. And we've sped this up a bit because it is quite a big FPGA, so it takes a bit longer to run. And then we'll flip over to the console and see our Hello World application. Oh, I forgot the locking. So I've got more work to be done. But it was 40 real cores running real instructions on this one FPGA. So that's where we are today. That was pretty cool. This is just a first step. As I said, this is just a proof of concept. This is just something we went off and played with. And we're really hoping to see more effort from the community, some collaboration around this. It's been a lot of fun. We've had a lot of fun on it in the last couple of months. We've got a lot more to add. So at the moment, we're just adding supervisor state. And so if we add a patch that Michael Newling worked on, it took him an afternoon to kind of add enough that we think will run some of the IoT OSs, so we could run one of those. A little bit more work, we should be able to get enough supervisor state to get Linux going. That should be good. And eventually, I'd love to see other people implement these cores. Let's see more of them on GitHub, maybe a Verilog implementation. Who knows? I would like to point out later on today, we have a BOF around all the open announcements that Ken made this morning. That's in the Harbour Ballroom at H at 11:20, so come along if you're interested in that. At that point, I'd like to hand over to Joe DeLaere, who's been a great support from us from Xilinx, to talk a bit more about the Alveo and OpenPOWER and everything around that. Thanks, Joe.
Thank you. Thanks, Anton. So a little gratuitous product placement here for Xilinx and Alveo. We are pleased to be working with Xilinx, pleased to be working with IBM and the OpenPOWER community on the Power ISA and the porting example that Anton worked on to give this product to the marketplace. One other thing I wanted to talk about is, coming from the FPGA industry, I've been in there for 20 years. His story really resonated to me with this project on microwatt. So from the Xilinx point of view, he's a distinguished engineer in software engineering. He comes from a software background, has never used FPGA, is not a hardware guy. In a short amount of time, he took our hardware, was able to port his design, create it in a very quick manner. This is really exciting for us because at Xilinx, this is our ultimate goal, is to have our products used by software engineers in the software ecosystem so they can harness the acceleration advantage of FPGAs. And so I want to commend Anton for kickstarting that. Putting this on the GitHub, Anton is seeding the ecosystem with this Power ISA soft core, and we believe that the community can take that and evolve it and drive the OpenPOWER and the open community with this solution. And hopefully we can add a hardware divide onto that Power ISA solution because FPGAs are really good at that. At Xilinx, we've been collaborating with IBM for a while, and we are going to continue to collaborate with them on data center solutions across all the verticals of data center, including compute, storage, and networking. And we look forward to collaborating more on creating solutions with Alveo that can be deployed in any server. So I want to thank IBM and Anton for this effort, and we look forward to continued innovation together using Xilinx solutions, Alveo, and FPGAs. So thank you.